Okay, everybody, part two. All right, I froze for a second there. Okay, so let's add in those rates. What was that? 10, oops, sparkle pen, that was serendipity. 10.8 times 10 to the negative 7th for that. And then what is our units on there? Does it give us units? Molarity per second. And then I think we had 5.4 times 10 to the negative 7th molarity per second. Okay, now check it out. This is why we choose wisely. Look at this. Your rate constant will be the same because it's the exact same experiment. This concentration is the same. We just canceled that whole piece. And then now check it out. Now, what's different here, we get to solve for m. I love it. So let's do the math here. And we kept our numbers nice and simple. So what are we going to simplify all of this to? It turns out we're going to have 2 to the m is going to equal 2. I love it. Genius. This is math even I can do. Let's solve for m. And that is the first power. So 2 to the first power is 2. That's genius. So our first order of business, when we choose wisely, we are actually going to solve for our order first. We want those exponents first. That's what we're going to solve for. So now let's turn right around and choose wisely again. And this time, what do we need to focus on? We need to solve for n. So how do we look at our data and figure out the perfect recipe to solve for n? We need, in this case, we need n to change. We need this one to change and this one to stay the same. Okay, so this is our m exponent. This is our n exponent. And look at that. Our actual rate is changing as well. So let's do that. Let's turn around and solve, and let's compare either, oh, look at that, we have two sets, either 4 and 5 or 5 and 6. Both of those would work. And then actually, if we look up above here, holy cow, these would work as well. I feel a color code moment. All right, so these first 3 you can solve for m. The second 3 you can solve for n. So this data is very strategic. We are solving for those exponents. That's on purpose. And why is this a really easy thing to do? Because you're in charge in the lab. You get to decide what your initial concentrations are. You're the one setting up the experiment. Okay, so let's do the same thing. I'm going to go ahead and pick 4 and 5, and let's compare them. So I'm going to take that rate 5 over that rate 4 and just start filling in, and you right along with me. Let's do it. So we've got the exact same concentrations here for our m, and you can either leave it as m or put in the 1. We've already solved for that 1. And then what do we put in for our second set? We're solving for n. And let me go ahead and put those rates in there. 43.3 over 21.6. And these are both molarity per second. All right, bust out your calculator. Just kidding. I think you can do this in your head. So let's look. Again, rate constant will be the same. You get to cancel it. Okay, these concentrations are exactly the same. You get to cancel that whole thing. And that simplifies to this with your exponent of n over this. So when you plug that into your calculator, shut the front door, you just got 2 to the n equals 2 again. So what does our n equal? 1. Okay, why is this so important? Let's go back and add this to our rate law. This means for our rate that our NH4 plus that exponent of 1 and our NO2 minus has an exponent of 1. That means that our reaction is first order with respect to that ammonium ion it is first order with respect to that NO2 ion. It is second order overall. Now, I'm just going to steal some of our cliffhangerness for our next round of videos, but what second order reactions mean is a collision. So what we just learned is this smacks into this in our mechanism. That's what that tells us. We physically need a collision of those two atoms for that reaction to happen. That will be our rate determining step as we go forward. So the order of the reaction is our whole goal in this video, is to figure that out. Okay, now let's go one step further and let's go ahead and solve for K. Let's find that rate constant. How do we do that? We can plug in any of our samples. Let's go ahead and plug in that rate number 1, number 2, it doesn't matter. I'm just going to choose rate number 3. And then we literally can plug in what we've just learned and solve for K. Now, grab your calculator, hit pause for a second, see what you get. For me, I get this. Okay, now I'm going to leave this unit list for just a minute. Our units will end up being a pretty big deal by the end of this whole unit 2 in kinetics. So we will definitely not just leave things without units, but we will tackle units in our later video. So what do you think? It's not too bad if you choose wisely and solve for order. And then what did we do next? Then number 3, then we solved for that K, which is our rate constant. So if you're savvy like me, what's your test question? You ask the rate constant, because you have to figure out everything before you can solve for your rate constant. So it forces you to do that whole problem. Okay, let's do one more. And this one is very much on purpose. It is almost identical to our lab this week. We are doing an iodine clock lab this week, and that is iodine instead of our bromide ion. So I chose this one on purpose. Let's really help you with your lab. And this kind of experiment has to be done in lab. You have to have something that you're in charge of. You will be in charge of these initial rates, and then you're going to literally time and figure out the rate for a series of reactions. And those series of reactions actually have to be quite strategic. Now that you know that we're going to solve for, what are we going to solve for? Let's write our rate law. We're going to have a rate constant, and we will have a bromate ion that has an exponent, a bromide ion that has an exponent. Notice that exponent is not 5. That is not moles. And our acid component, I think in our lab they call it a P, so let me just go for P. Okay, so we have literally 3 exponents and a rate constant to solve for. How are we going to do that? Well, what do we do? First, we wrote our rate law. Number 2, let's choose wisely. Let's pick experiments where 2 out of the 3 are the same, and then see if our rate changes. So if we look at experiment number 1 and number 2, oh, this is genius. Look, our bromate changes, but our bromide and our hydrogen stay the same, and then our rate changes. So let's go ahead and solve for that. Let's go ahead and do our rate 2 over our rate 1. So that's going to be our 1.6 times 10 to the negative 3rd over our 8 times 10 to the negative 4th. All right, and then let's choose wisely here. So we've got K, K. Our bromate is 0.2. Now I'm going to go ahead and leave off units. Like I said, we're going to tackle units. Don't worry, they're not going anywhere. We will tackle units. And then let's do 0.1 here for that experiment. And then 0.1 here for this one. Okay, again, choose wisely and your math gets really easy. It just makes you look smart to write all this stuff out, but really we just got to cancel all of that. So if we look at this math, we're getting to 2 equal to 2m. Aha, we've already solved for that. Our m is 1. Okay. So now we just plug and chug. We turn right around and do this again. Let's choose wisely again. So we've already solved for that first exponent. Let's choose again. How do we solve for bromide? Well, we're going to look for these two stayed the same. These two stayed the same. But our bromide is the only one that changed. So let's go ahead and compare that. And let's compare rate 3 to rate 2. I love it. So let's take our 3.2 over our 1.6. Again, this just makes you feel smart to write all this stuff out. But if we choose wisely, our math gets really easy. All right, so let's take 0.2 to the 1. We figured that out. And then we're going to take 0.2 over 0.1. That's what we're going to solve for n. And then look at that, p is the same. So what do we get to cancel out of all of this? Check that out, okay? And again, what we're finding is 2 to the n is 1. Okay, so both m and n are telling us so far first order with respect to that reagent. Okay, I love it. And now let's do the last one. So let's choose wisely again. We are going to compare, let's see, we need, son of a motherless goat. The only one that changes is 3 to 4, but crap, these are all different. Okay, but wait a second, shut the front door. Does it matter? No, because your exponents now, you already know your exponents. So go ahead and grab your calculator. Let's try this one again. Let's compare rate 4 over rate 3. And let's plug in our exponents. Oh, shut up. Look at that. Our rate stayed the same. Ah, wrong pen. So we've got the 3.2 times 10 to the negative third. If our rate stayed the same, there's got to be something deep here somewhere, right? Let's take that k for both of those. Okay, then we've got 0.1, 0.2 to the 1. Okay, 0.1 and 0.2 again. And now this time it's 0.2 over 0.1, and this is the one we're solving for. Okay, so we can still cancel this, and this is going to give us a 1. So let's plug all of that in on your calculator, and let's see what you get. What do you get to solve for p? Did I just not choose wisely? I may have entered the wrong data point here, y'all. I don't think we're supposed to have our data the same. Let's double check that. Well, maybe not. Let's just plug it in on your calculator and let's find out what you get. All right, so what do you get over here? Your math might be a little bit sassy. I'm going to grab my calculator and then let's see what we do from there. And maybe it just means that we've got to be good at our exponents. And if we wanted to make life easier, for example, maybe we turn right around and do rate 4 over rate 1, and now our life gets easier. So let's try it. Let's type that in real quick. My screen keeps changing on me. So I'm going to take okay. Okay, watch that. I'm going to get 1.25 times that 2p. Remember, our goal is to solve for p. So I'm going to go ahead then and divide my 1 by 0.25. Okay, so I'm going to get 4 equals 2p. Now we're talking turkey. What does our p equal to? Okay, so all of these should give us the same answer. It just depends what your math is going to look like. Would it have been easier to compare 4 and 1? Probably. But you should still get to the answer if you compare any of them. Okay, so holy crap, we haven't seen a 2 before. What does 2 mean? Second order. Okay, so total then, what is this full experiment? This rate law then is actually first order, second order. So total, this is fourth order. Okay, that is a little bit sassy, isn't it? Let me add a page and let's go ahead and I just lost my whole thing there. I want to add a page. I got to get my keyboard up. I want to add a page and then I want to go ahead and just solve for k. So you start while I am trying to navigate the mystery that is my iPad. And there we go. We got one. All right, so let's go ahead and solve for k. Let's take any of our rates and let's go ahead and plug in. Let's just take rate number 1. Why not? And let's solve for k. And now we've figured out from that first one that if we're taking that first experiment and we're plugging in our numbers, we're going to take 0.1, 0.1, and then our 0.1 squared. So then let's turn right around. Let's double check our data table. Did we just put in the right? Yes, we did. Okay. So let's turn right around and solve for k then, and let's see what you get. So for k, I get 8. There is no right or wrong answer for k. Your data will give you k. There's not a table you can go look up and see if you match k. You have to solve for k at the end. Your data has to match k. This is all data driven. Just like the order of your reaction, all of that is coming from data. You can't get to your reaction order without actual lab data. I love it. So this last one here is very similar to your iodine clock reaction, which is what our lab is for this week. So I'm going to post this video under both lab and lecture, and then we'll try some more of these on Zoom on Wednesday and lecture. I'm super excited. We'll see you guys soon.